Hello, everyone, and good day. Welcome to the ITU AI and Machine Learning 5G webinar series. Thank you very much for joining today. My name is Thomas Baskoro from the International Telecommunications Union ITU, and it is my privilege to introduce today's webinar. The AI and Machine Learning 5G Challenge is organized by the ITU, which is a United Nations agency for ICTs. The mandate of the ITU is to allocate frequencies to services that use the radio spectrum, to develop standards, and to assist developing countries in setting up their ICT infrastructure. This challenge is kindly sponsored by Xilinx, and we are grateful for their sponsorship. The challenge aims to create a community that will solve network-related problems using AI and machine learning. And now I would like to introduce the speaker for today's webinar. Today's presentation or webinar is going to be given by Henning Sanek. Henning has the Network Automation Research Department in the Standards Unit of Nokia Strategy and Technology in Munich, Germany. He received his PhD degree in electrical engineering from the Technical University of Berlin. Afterwards, he joined Siemens Mobile Networks as a senior research engineer. In 2014-2015, he became the head of cognitive network management for Nokia Networks Research, as well as acts as the coordinator of the research and standardization work. His team has been continuously involved in national and international funded research projects. His current research interests are in beyond 5G network management and orchestration. He has published 80 papers and 30 patents granted or published. He has been co-editor and author of the book LTE Safe Organizing Network, which was published in 2011, as well as the co-author of the book Towards Cognitive Autonomous Networks, published in 2020. Today's talk, Towards Cognitive Autonomous Network 5G and Beyond, will discuss the necessity for network management systems which needs to be cognitive. That's to say, being able to conceptualize as well as contextualize itself in its environment. In this talk, several use cases will also be discussed, which includes predictive location-aware network automation for radio, Planar, which enables coverage and capacity prediction in the digital twin of a sliced 5G trial network. Welcome, Henning, and good afternoon.
Yeah, welcome to everybody. Welcome to us.
Thank you so much for taking time and to give us this interesting talk. We are looking forward to hear what you brought for us today. So the floor is yours.
Yeah, first of all, thanks to Thomas, Vishnu, all of the organizers for inviting me. It's really a great opportunity to present in this prestigious meeting series, and in general, this ITU AML challenge is, of course, a very important and great idea here to broaden the base for this technical community. Then maybe before I start, I really like to point people to other talks in the series to which this talk is related. So last year we had talks here on this Open 5G RAN and also on the 6G radio, for example, from my colleague Jakob Heudis in Nokia Bell Labs. And only, I think 2 weeks back, we had a very interesting talk from Mel on towards autonomous 6G networks and the role of advanced machine learning, which you can consider also like a baseline. If you have not looked at it, then I encourage you to do so. Also, we have ongoing this trustworthy AI meeting series from Wojciech Samek, which is also very nice complementing this, and I really encourage you to look at that. Yeah. Okay, so let me share my slides. So I hope you can hear me well and see the slides. Yeah, so my talk is entitled Towards Cognitive Autonomous Networks, CAN, 5G and Beyond. And as you can see, this is joint work in particular with Stephen Manier, Jan Ali Tolpa, and Martin Kayo from my team, but also actually across some other teams in Nokia Bell Labs and Nokia Standards. You can actually see there's no AIML in the title apart here from the logo. And this is on purpose because I really want to motivate that the characteristics we want to enable are actually this cognition in networks. Yeah. Then also what was quite interesting when you look at the series of talks, there's a lot of towards in the title, yeah, also in my talk, but not only in my talk. So it means also, of course, we are here at in the middle of a journey. Yeah, I think we have a good baseline now also with what we have done in 4G with the self-organizing networks, in 5G increasingly now we're moving actually to ML-enabled functions. but of course, this will take us up to the, let's say, the 6G arena, basically. Yeah. Okay, so let me start by first doing a bit an analogy to the human cognitive decision making. So it's like, you could say, in a way, bio-inspired approach here. So here we have a perceptioning reasoning pipeline. Yeah, first of all, you sense your environment, you conceptualize, and this of course relies a lot on the memory, on the previous experience you have had, on what you have learned already, right? And then you have the opportunity to, first of all, read labels, but then also relabel if something changes. Yeah, if you learn like a new, kind of a species or so. I think in our book, Stephen introduces this example of a lion, right? So first of all, you see a lion, you need to identify it based on your experience. But then the important thing is also to contextualize it, right? So it's a big difference if you see a lion or meet a lion in the zoo, in the African wildlife, or you just see a photo, right? So all of these things really, contribute to this whole understanding of the situation. And this whole perception in the past, I would say, in networks or in general in technical systems has been actually quite underrepresented. So typically we have encoded knowledge into pretty fixed knowledge bases and then only over time updated them and focused more actually on the reasoning. Yeah, of course, the reasoning is then also crucial when we want to take not only actions in terms of very quick understanding of the situation, like should I run, should I hide or so, but really organize ourselves, make a plan, reason, infer the right, deduce the right decision, and then really do a conscious action. Yeah? And that's of course also our goal in technical systems and networks, to really come to very, let's say, well-founded decisions. Yeah, and then also, as you can see here, update the knowledge base, our memory continuously as we do so. Yeah. What I think is also very important, and when you look at various references in technical systems, but with communication networks, we can actually do actions along the full cycle here. Yeah, as you can imagine, for human, it's like, if the doctor hits your knee and you have this reflex action up to this very quick reaction when you drive a car, need to push the brake. But then, like I said, also this very conscious decision, which new job you should take or so, right, where you have a lot of planning and reasoning. So we have actions at all levels here, right? And this actually we have, or in fact, we should have also in technical system communication networks, right? And of course, it depends, and that's exactly what we want to push. It depends on the level of perception, the level of reasoning we can achieve. Yeah. So in the past, for example, we had, for example, during a maintenance window, operators were doing cell resets for a certain cluster just to be safe that the next morning they can be sure that they work again. That, of course, is a very, in quotation mark, dumb action, right? So it's really even a scheduled action, yeah. And then you could have reflex action in the sense of that you have, fixed thresholds, and you basically some very simple rule fires, and then you close the loop and you start again, basically, yeah. Okay, and then of course, when you look here at this loop, this is of course something. Even if we have a complete perceptual reasoning pipeline for one iteration, of course, this means also that again, then we resense the environment, we reason. So it means we close here the loop externally, basically. Okay, then when we go now further to technical system communication networks, you can basically see here on the right-hand side what I just introduced. The simplest form is that you have here some set scheduled action or just a sequence. And the next level is here that you detect a certain network event by a simple threshold, for example, then correlate the events, right, really across, for example, different KPIs, or spatially and also temporally correlate. And then, of course, we have already a very big step in terms of this simple diagnosis, right? So basically, if you go from, for example, simple alarm correlation, then really to interpreting the meaning of these alarms and so on. And even more so, of course, if you really understand the context of, for example, this alarm in a certain network situation, right? Does this alarm hit a backhaul link versus wireless backhaul versus a fixed backhaul, for example? And then we also, of course, can do the same things like we do as humans, also in anticipating, okay, what could happen in the future along the standalone and correlate events, and then also, of course, also enable diagnosis similar way as we have enabled here. As you can see here, autonomy basically, so in the sense of that we automate and then also in the end fully automate the system is actually, we can do it every level here basically. Like I said, you can have a pretty, in quotation marks, stupid system, but which has a high degree of automation because a lot of things are encoded in rules and then those rules fire. But the idea is, of course, to really push the level higher and make the system really cognitive and autonomous. On the left-hand side, you see the definitions. So basically, autonomy only refers to the fact that I have a black box. And in this black box, there is a certain logic, and without any external, involvement, I can actually, the system can actually come to some conclusions basically and propose an action basically. In terms of the cognition, this is really this advanced perception reasoning pipeline, but it doesn't mean necessarily that, of course, the behavior has to be autonomous. You can also still include an open loop way of doing things. And so that means those things are really connected, of course, but in principle separable. And then we have also the well-known concept of self-organization. That means that then if you consider this black box, basically that, inside the box, you have some emergent behavior that the system converges then to a certain steady state, again, really on its own, not by some external influence, basically. Okay, now then, when we go then to basically tools and how we can implement such systems, let's talk about then the cognition and communication networks. When we have a static model, first of all, in which we call classic AI. So that means the human develops a model, right, and encodes something. And then we can, for example, make this model adaptive to deployment by probabilities, like this well-known Bayesian networks approaches, or things like Markov logic networks, when we incrementally, based on this inputs, we adapt the probabilities. Still, this is then fixed, right? And if we really want to fundamentally change the behavior, we need to, update. The human needs to introduce new rules, or we need to, for example, rely on software management to include a new release, basically. Okay, then learning. I mean, here this is a well-known definition from the textbook, basically. So we have a certain task T, right, where we can measure the performance P, and then this improves via learning with this experience E. That means we parameterize the model with a certain loss function, and then iteratively update the model with this experience. So it means we really ingest data, we learn certain patterns on the data, so like clustering, unsupervised learning, or we learn how that data matches to label we have given, basically. So the model building is really in situ, and the human rather needs to worry then on providing the proper training data, but also then, of course, how to deploy the model, and then how to put this into the, say, the inference path. What you can see here, that also what is already important for us then in standards. Here, of course, you have the typical interfaces, right? So that you need to define what are the input KPIs and then the output CM parameters, and do this, of course, also in a multi-vendor, ideally standardized way. This is, of course, the same here on this inference path. But then in addition, we also need to expand basically this interface, simply because we have specific requirements on the training data or the training location, like training data granularity, and then where actually to execute the training, because it might be more compute intensive. And then we build the model, and then of course we also need to worry about, where and how this model is actually deployed, and then also of course to leverage capabilities that I can deploy a model, learn in one location, of course, to several locations. Also, take really advantage this up to things like transfer learning, where I then extract, let's say, a part of the model and transfer it to another deployment new location. Okay, now let's look at this separation of the cognition and the autonomy, and also how they interrelate along this taxonomy. So typically, when you look at taxonomies of these levels of automation, you will find actually only one dimension where, in fact, those two dimensions are somewhat amalgamated. And also what you can see here is that, of course, the diagonal axis here, this is the really important one in a way. So these capabilities are connected, but still I think it's quite useful to look at them, to understand them really in this separation. Yeah? Here on this axis, you can see what we just introduced. So you detect an event, you correlate, you diagnose, contextualize, and so on. On this axis, on the autonomy, we go then from manual, as you can see. So you have everything, human detects something, human correlates, you diagnose from experience, basically, and then also based on your knowledge, based on your experience, you look somewhat into the future. Yeah. When we go to assisted, so assisted execution, and then also the human is still involved in the execution, of course, it means basically that we use the system to selectively expose certain events. So meaning, the machine is of course able to analyze hundreds of KPI curves at the same time. A human could never do. So there's also already a big value add to say, okay, I expose to a human. And then also the contextualization typically is then a good, say, visualization, so that a human can really make then this future projection and also act basically on this information. Yeah. When we go further here to partially automated, means that even at the lowest level, we can of course tie actions to the detection. And then from here to here is of course, like I mentioned, already a big step, right? So meaning here we have the machine actually be able to map the incoming information to causes, yeah, and based on the rule base, and then also to automatically react basically those rules firing, and then some action is tied to it. Yeah? When we go to contextualization, here already the learning then starts basically with profiling. So meaning we enable the machine to, for example, in the cellular network, to really identify typical profiles for cells, for example, along bank holiday versus workday, or our time of the day, and so on. But and really do this not based on, again, knowledge operator or human operator has, but really do this for the concrete deployment. Yeah? And that, of course, you can also to some extent extrapolate, and then also come even to a certain pro-action for the future, right? So that you even react in advance, because here you understand where the operating point is moving. Yeah? When we go now to the automated, really means that at the machine level, we have the full execution. It also means that here we say it's actually not really applicable, because you will never be able, for example, for mobile network, to have, let's say, full complete rule base, right? So that means to achieve this, there is already, you're at a level where you actually need the machine to learn from the data. Also, we argue that it does not really make sense, for example, here to, even if you would have the full rule base in terms of the supervision, which then also goes to the machine level, to have learning there, but not at the execution level, basically. Okay, what happens here is then basically the human labels the causes identified by the machine, and then also the machine can, choose between different possible actions. And of course, you can again imagine you can do the same if you have then a projection on the future, do also pro-action selection for this outlook, basically. Yeah. Okay, and then again going further, partially autonomous, meaning that the machine also takes on partially the supervision of the whole process. So that means also things like model-free techniques, reinforcement learning, also transfer learning, which I mentioned, where the machine is then able also to decide to transfer a part of the model then into a new context. In the contextualization, then you can think of the machine learning actually new policies for this governance, right, based on earlier experience, right, in terms of the supervision. And again, then also even there look into the future. Yeah? And then for the autonomous, of course, it gets pretty futuristic in that on a diagnose level, then the machine would also offer explanations why certain decisions have been taken. So really instrument also this, say, more advanced techniques. Then also at really, let's say, machine reasoning, and also this trustworthiness, which is also adding, yeah, say, a robustness to the explanation, also fairness considerations. And then, like I said, ultimately here you're really in that the machine can do, you know, everything up to the full reasoning, basically. Yeah. Okay, and then in the following slides, I'd like to go through this Planar case study, which approximately you could position here, because there we already talk quite a bit about prediction, and we also tie, let's say, automated or fully for that use case, fully automated actions to the diagnosis we do. Okay, so let me talk about Planar case study. So this is called Prediction Location Aware Network Automation for Radio. Here we had the opportunity to work with colleagues in this 5G network slicing testbed at Hamburg Harbor. You might have heard of also, because this was actually used for various undertakings, for example, also in the 5G Monarch project. The idea here is that we have an outdoor testbed where we have actually barges moving regularly, let's say, on certain control missions in the harbor, so from the Hamburg Port Authority. We have, this is actually an IoT use case where actually the barges emit or actually have emission sensors on them, which emit some transfer data to a central entity. Then we have an ultra-reliable low latency use case where a certain important traffic light here is instrumented and controlled remotely. And then we have actually all kinds of, you know, employee communications here in these two cells in this harbor area. And here an experimental base station is actually mounted on this tower, and that means all this whole harbor area is then accessible or covered for this to execute those use cases. Yeah. Okay, what we collected there were slice-specific BTS, so base station KPIs, so physical resource block usage, throughput latency, and then also the UE measurements of the, say, fixed UEs, but also then particularly the barges, and also here the RSRP, RSRQ, and ping measurements from the application point of view. And the good thing about this testbed was it was pretty long-term, so meaning we could collect long-term data, but at a very fine granularity, which is also, let's say, not typical. When you take a typical network management system, you get something like 15 minutes, 10 minutes, 5 minutes if you're lucky, but not at that granularity. And this was actually joint work with the Technical University of Munich. Okay, and then we were actually, like, typically when you go through the data with data scientists and domain experts, we were looking and seeing what actually we see there in this experimental testbed. And there were certain effects, of course, when a barge comes close to, let's say, the edge of the coverage. Yeah, that was an effect we have seen. But also we have really been seeing then certain shadowing effects. Yeah, here you can see actually perspective, actually in the digital twin from the perspective of one of those ships, where you see actually the tower here. In some areas you don't see it, but then you even have then shadowings from this buildings here. And the idea was, of course, that we use now this advanced technology to improve the service reliability, but on the other hand, of course, don't make too many compromises on the other slices, which are also present, and also don't over provision basically just from this installed base we have there. Here you can see along the trajectory from the barge, right? The RSRP has the drop actually also missing data, as you can see here, and also the ping times then have extreme variability, also simply drops then basically. You can see there's really, in part of the path, there's really a problem. Okay, so what we did then was, on one hand, prediction of the mobility, but then also on the other hand, the prediction of the network QoS. So we have created this radio propagation map. So based on this UE measurement, so this GPS position, RSRP, and used here a feed-forward neural network to do this. Here you can actually see how these two cells here, the RSRP in a heat map, covers actually this harbor area. You can see along these waterways that there will be handovers. And yeah, of course, here one or the other cell will be then the dominant one. And then we also did a mobility pattern prediction, just looking at these positions reported by the barges, and used the convolutional neural network to predict the barge movement. And here you can see an example where blue is here this input sequence. So this is really the inference data we feed to the system. This is the ground truth. You can see particularly here, and also the prediction. So you can see that the mobility model is not just, or this prediction model is not just something, like a prediction of a time series or an extrapolation of a time series, but by monitoring or feeding it a lot of data here to this model, we can then identify, let's say, typical movement patterns like these turns along the quay, or also the barge turning around at certain locations. Yeah. Okay, and then we combined those two models, and then we're able to predict up to 90% of this, let's say, low RSRP events, which then also, let's say, could lead or have led to radio link failures. Yeah, and also then with a certain look ahead time, 40 seconds, which gives us then a certain amount of time to act actually when we have the capability to do so. Yeah. Okay, then we had the opportunity to obtain a full 3D model here of the city, in particular the harbor area. So meaning, like this topology, the waterways, the streets, the building heights, and so on, and could move then this network topology and also the configuration into a radio simulator. And then also we were taking basically this real traces of the movement into the simulator, from the testbed into the simulator. And then in the simulator, we had then the radio propagation model, basically off the shelf, what we usually have in the simulator, and we could actually reproduce the coverage issues from the real testbed. Yeah. The nice thing, of course, of having a digital twin is then also to actually implement features you don't have yet. Let's say in the testbed. In our case, this was this beamforming. So meaning we have here we could then simulate 4 beams for each of the cells, basically. Yeah, and only later then we deploy this actually into the tower, basically. Okay, here you can see then the overall setup. So this is also a demo we have shown at the IEEE NOMS. Here's the YouTube link. The video is actually much nicer than what I can tell today. Yeah, but like I said, I tried to use this also with example to show a bit the bigger picture. So as you can see here, we feed in the test scenario into the simulator. We record the movement. Here we have a data collector. So this Planar management, of course, would be then really something we can run in the real testbed, or let's say then in any other settings. We have a data collection. We have here the mobility prediction, which is then chained to the QS prediction. And then with those predictions, we can, in the real testbed and the digital twin, we can change the transmit power. And only in the digital twin, we can change the beam adaptation, and then actually redeploy the configuration, and then let the simulator recompute basically this radio conditions. Okay, then here you can see actually the let's say the real demo GUI, where you first of all see the throughput and the RSRP, and you always see that with the measurement and then also the prediction, which is then 40 seconds ahead, or if you whatever you want to put it, or 40 seconds earlier from this. For example, here from this incident, you can see that basically, okay, first of all, you can also see here the cell ID. So we have 2 cells, 1 and 2, and 0 means basically that we have a radio link failure. Here you can also see that we have actually had a handover successfully executed, without any quality impairments. And then you can see also this slight degradation in the RSRP. But the system then projects actually that there is some, say, RLF ahead. And in fact, by then adapting the system here in the digital twin, we could actually avoid this this radial link failure, right? And in this case, we did this then by a transmit power change for one of the cells, and then also for the same cells adapting one of the beams, basically. Yeah. So in principle here, what the capability we have is, like I said, changing transmission power, activate or deactivate beams, and then also do tilting. And the idea is, of course, that we can then, in general, allow higher thresholds and then reduce this over-provisioning. Anyway, introduce a bit more robustness so that, you know, actions we take here for one of the slices also doesn't affect the other ones. Yeah. In the end, of course, what we don't show here, of course, this is really about it is about managing a slice. Yeah, but in the end, of course, it's also changing physical parameters, and of course, then, for example, you might have then actually conflicting decisions for example, now for an entity, a UE or a population of UEs on another slice. Yeah, that of course also would need to arbitrate in the real system. Okay, then yeah, let me quickly also introduce another project we're currently working on, which has actually, yeah, you could say quite a bit of synergies with the Planar I've just introduced. So the project is called KIC, which is a German acronym for Artificial Intelligence for Campus Communication. And in this harbor example, we had an outdoor, say, industrial network. Here we go indoor into a production plant, a manufacturing plant. And the idea is also similar. If you imagine that in the harbor example, we had barges. Here in the manufacturing scenario, we have, for example, autonomous guided vehicles with a certain mobility. Sorry about this. Of course, the idea is here, like we collected information about this barge movements in the harbor testbed, that we can somehow instrument by using the data, you know, what are really the requirements, for example, looking at AGV movement patterns, but also looking at certain requirements in terms of the machines or the production cells which are located here in this factory to actually, let's say, complement this, let's say, AI/ML-based management operation of the campus network. Yeah, and yeah, in general, so this should be a kind of a cross optimization, or it actually is, like in the Hamburg Harbor example, already a bit of a cross optimization. The idea is here that, particular for the smaller deployments, you know, when you consider SMEs, that there's really a certain simplification here, yeah, because you have only remotely, you might have then really network operation personnel, not on site, of course. And in general, you know, many small deployments, yeah, where you don't have the capability like a mobile network operator, for example, and that should really support this economic viability and then validate these methods in this different setting, right? So, and then contribute to this overall vision, of course, of an automated factory. And you can see a lot of partners here. So that means it's really a cross project from, you know, industry players, networking players, and academic and SME enterprises. Yeah. Okay, then I was already talking a little bit about, again, going a bit to the bigger picture here. I was talking about, for example, this arbitration. So what we have shown in this Planar demo is actually this, what we call here inner AI. So meaning the choice of certain algorithms, you know, we have in a way off the shelf, and we take and adapt to a certain telco or telco management use case. Then what we have also shown is this yeah, data acquisition and how we ingest the data, basically how we yeah, create a model from the data and execute the model, basically. And then also how we generate certain domain-specific action like this transmit power and beam change from certain outputs of a machine learning model. So basically this three areas here. What you also need to consider, of course, is this execution, right? In the real system, we might not have everywhere the capability to execute sophisticated machine learning models. So that might be also constrained, for example, where to place training capabilities and in general, where to place certain network functionalities. Yeah. Then here, this arbitration, we call it inter-AI. So meaning that I might have conflicting goals, like for example, different algorithms proposing changes for the same cell, affecting then the same or different slices even. Also conflicting goals, for example, in the sense of that an operator might want to optimize the whole network for energy saving versus optimizing for perfect performance all of the time, right? So you have the certain trade-offs you need to impose on these algorithms, which also brings us to the area of governance then. So governance is everything where an operator expresses a certain high-level intent, and then I should try to map this to some concrete policies. I was also mentioning this initial matrix in terms of the supervision of this different machine learning algorithms for each individual algorithm, or each individual type of function, mobility robustness and coverage capacity optimization, but then also, of course, across those functions. And then we have, of course, this framework areas like fitting this into a legacy telco architecture. When we talk about AI, it's also always about ethics or certain, bias we see in the system, which may be disadvantages to certain users or so. And then, of course, also security and sustainability here in terms of the execution, of course. Okay, then let me outline a bit the 5G and beyond, basically, or where we are here in this, moving to the 5G evolution and then also towards 6G. So if we summarize in LTE or the early 5G, we had the self-organizing network concept, meaning we have rule-based management functions, and we have, let's say, conventional software management where we roll out network functions. And then if we identify certain issues in operations, or we simply improve our operational knowledge, we adapt them and then roll them out in these release cycles. Here we also need then a pretty significant layer of SON operation, like I mentioned, rolling out this policies basically, which then arbitrate here across different function instances or different types of functions, and then also expose, of course, to the human, first of all, where the human is still needed in execution, and then also, of course, the interfaces to supervision. If we go then to the 5G evolution, we call it cognitive network management. That means we have certain learning function where also the idea is that then to some extent the function themselves, they can interact, and this operational layer gets thinner. The idea is also that basically here when in software management, we have things like DevOps, meaning that we have, let's say, at least a process path from operational experience again to the R&D basically, right, to improve on the fly. And also we can say that those functions are also, when you look at efforts in 3GP, for example, with regard to data collection, that they're more, say, data driven. And then if you think this further, we argue that in the future, when you also think about this things, I was mentioning already my colleague Jakob Heutes, AI, so like an AI interface, or an interface designed through AI, let's say, then of course you can imagine that some of the function will actually move then into here the control plane, and then the role of the management layer changes to actually managing the training and exposing basically the required information to the human. We call it here comprehension, or you can also say explainability in a way. Yeah. Okay, to make this a bit more clear, I wanted to also highlight a bit the development across the use cases. First of all, when you just visually look at that, it's clear that only not all of the use cases need, in fact, this machine learning or this cognitive support, right? They're pretty simple use cases like this neighbor relationship setup, where in theory you could learn actually the behavior, or working on this neighborship list. But I think in reality, probably here still a rule-based solution is sufficient. For other use cases here, maybe some of you also know very well the SON use case, so I'm not really go through all of them now, but you can see that here you move basically from from a rule-based variant of mobility load balancing to a machine learning-based one, and similar for others. Here, for example, in the days of SON, we could actually not really do proper cell anomaly detection. So we had things like sleeping cell outage detection, so really detection of catatonic cells, which are dead basically, right, where you have no traffic. And to even identify cell health, you already need some profiling, some anomaly detection capability, basically. Then when you look also at going then for the future into the next level, you can see that here, this blue area, cognitive network functions, where then, for example, things we have shown like the coverage and capacity optimization is actually combined then with the radio resource management, or for example, here the mobility management includes then the mobility load balancing and the mobility robustness. For the virtual network function scaling, there will be functions which have, let's say, built-in scaling, right, when you scale in and out. And then rather the overarching capabilities, like when you scale the instances down and up, or you place instance, of course, you still need a overarching capability, which is then more in this category, basically. And also for the radio here, for example, traffic steering, when it's about different radio layers, so really independent, also independently managed layers, and small cell versus macro, then it's still at that level. Okay, and here you can see actually these connections, and again here, of course, the new management functionalities, then this management of training, of course, management also of inference, of comprehension. So all of this tasks you need when you have an AI-based network or network management function around. Okay, then I think the Planar is basically here. And then we can think about, okay, how to leverage this then for this future scenarios. Okay, conclusion. So I try to formulate here a few takeaways for your consideration. So we have, first of all, this cognition autonomy. These are crucial, but to some extent separable properties. So we need to understand the system concepts and context to be really able to do this decision making at the machine level. Actions can be taken at any step in the cognitive process, so it doesn't mean that we need to have the full, say, reasoning capability to be able to close the loop. Yeah, we can do this further, but of course we should do it in a, let's say, sophisticated way. Yeah, but it's always about the needed depth of diagnosis, right? So for example, if you reboot your Windows machine because you have a problem, you're not interested to do, let's say, R&D contribution to Microsoft, you're rather interested in getting the machine back to work. So for you, this level of diagnosis, something doesn't work, you reboot, it's enough, right? So it's a very stupid action, yeah, but it's enough. And for other areas, we always need to find the right level. When I need to choose an action, what is the diagnosis depth I need to go to, basically, yeah. So that's also why I don't typically like the term of root cause analysis, because it's often not about the root cause, but it's really about the right cause level to take the action. Then AI enablers, I was introducing this data execution action pipeline, and then this inter-AI and governance, which are more the, let's say, system level and then human facing areas. Inner AI is particularly relevant, I think, for the research community. What are really good algorithms we can adapt then to our telco use cases. AI requires then also some expansion on this interfaces to data for this training data instrumentation, and then also new ones for the model management. Yeah, and when we go now from the 5G evolution, 6G, we see that ultimately the cognition autonomy will penetrate more the U and the C plane. AI is, of course, the technology area to enable this, and then the M plane will take a new role managing the AI on the U and C plane. This is, of course, also a question of the whole process. That's why I looked at this sequence of use cases there. So we need to integrate and we need to replace certain legacy function. And then, of course, it's not that everything moves there, but some SON and CNM functions will remain. Okay, so why are we actually doing all of this? It's really about performance improvement of existing network management functions, but then also enabling new functions. So for example, when we moved from semi-automation, let's say, to SON, we could not before we could simply not do things like mobility robustness, because humans or simple scripts couldn't really identify the conditions and do this on a large scale. Yeah, this was already possible. And then when we moved from SON to cognitive network management, again, with the capability, for example, of profiling, really learning an operating point, then only we can do things like cell anomaly detection. Yeah? And then from the operator point of view, the idea is, of course, that it appears as a simplification, meaning that like I was outlining with this initial matrix, that the operator really role shifts from execution to supervision more and more, but in this, say, stepwise fashion. Yeah. Okay, and yeah, last but not least, I like to point you to our book, yeah, on which actually also the seminar is presentation is basically yeah, inspired or based. So here you can see that we have the background. I was only, of course, able to go superficially through. There's a lot on this modeling cognition and these two areas of classical AI and machine learning basics. And then we go through, we go through all of the, yeah, let's say FCAPs, traditional configuration, optimization, healing, operation areas, and present, different concepts, going far beyond, of course, what I could present today. And of course, we then also look into the future. And like I mentioned, the keyword here is still towards, yeah, because of course we are in some aspects still at the beginning here. Yeah, yeah, here you also have some recent journal and conference publication tutorials from my team you might want to check out, which, as you can see, then also go into this various technology or also network domain areas, like, for example, radio and edge cloud. Yeah. Okay, and with that, Thomas, Vishnu, I hand it back to you, and I'm ready to take some questions.
Thank you so much, Henning, for this nice talk. We have some questions, so I would like to welcome my colleague Vishnu. Good afternoon or good evening.
Thanks, Thomas, and thank you, Henning. I think another excellent talk. By the way, for the audience, Henning is not new here. He has been helping us, and this is almost the third or so talk that he is giving for ITU in this platform. I really like your the way you put together this talk, and especially the digital twin concept, because if you look at the KIC project, which you talked about in your last presentation also, and this Hamburg seaport project, it is very clear that you have really used this concept of modeling to a large extent. You have collected the data and modeled it. That's a very good exercise. And this question of digital twin. So that brings me to the question of digital twin. The question is that actually this question I had as well, and Alex is asking this question, that how do you reflect this real-time updates to the digital twin? So the way I look at it is that, of course, we analyze this in the context of focus group, autonomous networks, and the way we look at it is that you need a way to somehow reflect the reality to update the digital twin. I think that's exactly what Alex is asking. Could you tell us how, for example, in the case of Hamburg, how do you update the reality to this digital twin?
Yeah, that's of course a very, very important question, and glad that you're asking. Also, I mean, okay, maybe let me start by telling that the people are really working in this domain. They first try to actually establish also, let's say, a common model for the mobility prediction and actually this QS prediction, right? But then realized, okay, we're only doing actions, of course, affecting the network QS, or basically, changing network parameters. So they really separated those, yeah. So the mobility prediction and the QS prediction, right? So that means basically what we have done is then feeding in the mobility traces, right? And then of course at some point you assume that this traces actually cover enough the you know, this what you could expect here, the movement of these ships on the waterways for a certain time period, right? Of course, you're right. Then, for example, I mean, this is really, I would say, exactly when the, you know, when the some key characteristics of this digital, of this environment changes, which is relevant for the digital twin, then of course you need to update. Yeah, but if you consider, you know, streets, waterways, even this movement patterns, they're actually very stable. Yeah, so they have also certain, you know, say typical behavior. That's of course also the reason why we can actually do it so nicely as we have shown, right? So it means this is of course based on some knowledge of this environment. Yeah. And then, of course, you could argue that you could design then a system which regularly checks, okay, how much concept drift we have then in this movement patterns, yeah. And of course, here, I mean, or let's say the simple answer for this test bed is, of course, that was not really our concern, right? Because we had a predefined time period, yeah. Over the time period, we could collect a lot of data. You know, put it all, let's say, in one analysis, one model, and live with it, right? And of course, the question is particularly valid when you say, okay, we move to a real system, then exactly we need to find the right point in time when we retrain, let's say, this model for the environment. And of course, then in the, you know, in terms of the digital twin of this radio simulator, there anyway we, you know, constantly do this update based on this baseline assumption of the environmental model, basically. Yeah, so in that sense it's separated at that level. Yeah.
Mm-hmm. Thank you so much. I think to me this is a very important part of your solution, because it kind of marries this environment of the port, seaport, or the campus networks with that of the communication network. Let's go to the next. Yeah.
Maybe what I can add, even, I mean, this is actually also a bit like a school of thought question, right? Some people say, for example, everything you can infer from network internal data, right, you should use, and then of course adding external context sources introduces complexity. Yeah, for example, exactly this retraining complexity. Yeah, so that means also probably we should not be too proactive and say, okay, I have a network system and now I try to, you know, introduce weather, whatever context sources, event calendars, and so on. So all of this is a good idea, right? But you always need to really understand what you're doing in terms of the, say, external context domain. Yeah. So that's really a trade-off, I would say. Yeah. And or put another way, the more you can rely only on, you know, your network internal data, also in terms of the separation of the systems, of course, it's also an advantage. So it's really, I mean, you need to find a balance. Yeah. So it's not that we advocate, okay, you should always look heavily only at this context sources. Yeah?
Understood. Thank you so much, Henning. The next question, actually, slide 3 and slide 5, both slides. I had this question as well, and Stefan is asking this question for me. so thank you, Stefan. He's asking the actions, about the actions. If you go to slide 3 or 5, I think either of them you will face this question. That, yeah, so if you see this slide, on the right side you can take one or more actions, but on the left side you have this whole set of steps that you have given, which are very nice. But for action you just have take one or more actions. Why is it so? So my question was a little bit more futuristic, that whether you could cook up some actions based on your cognitive nature. Can the system cook up some actions or come up with some actions based on the context or the modeling that you are doing? Yeah. But I guess Stefan's question is a little bit more simpler. He's asking, can we use a recommendation engine? So either of a, could you tell us why the actions are more complicated?
Yeah, not sure if I got the question. I mean, of course, I mean, now if we go again to a real system, yeah, like I mentioned, I mean, let's say I would categorize it this way. The hard part is really the diagnosis, also connecting diagnosis with the context, right? And then typically, and we have also done such experiments, for example, having a certain utility function which action you choose, right? For example, you might have a pretty simple action like resetting your cell or even rebooting your base station, but it might be in the end quite costly. Yeah? So it's like a risk management analysis, right? And so typically you can actually put those decisions quite nicely in like a decision tree into some you know, say rules, set of rules. So there, like I said, from the research point of view, I think this idea, first of all, to come to this course, this is actually the hard part. Yeah, then selecting the action, it depends, of course, on your use case. Yeah, but this is typically in our or the system we have looked at, not the hard part. Then, yeah.
Understood.
Then,
Understood. Yeah.
Should I also answer on this recommendation engine? Maybe it's also a bit simply a terminology thing. Of course, when I talk about a rule base or then also rule engine to execute, it is basically, I mean, you could say also then the recommendation engine, if you encode there, then this say cause or this say, yeah, detection to cause mapping, yeah, and based on the cause, you formulate the recommendation, which means that one rule fires, yeah. So, like I said, it's a bit a terminology thing. So typically we talk very causally about rule-based approaches, where you basically have a more or less, yeah, like I've shown it on this other slide, fixed encoding of this mapping, or then you have this approach that you learn from the data. So.
Yeah, understood, Henning. Actually, that's nicely taking us to the next question. We are kind of running short, but let me put you this: the transfer of what we learned from the digital twin and the models that you create. Could you tell us a little bit about this nature of transferable? In the context of RAN, rule-based feature is transferable, but ML-based feature performance is highly context sensitive to data and training. So what is your take on that?
Yeah, I mean, exactly. This is, yeah, let's put it that way. I would say if you, I mean, right, so often you don't even have the choice. If you go to this slide, right, I mean, this is not completely interchangeable, right? So I have cases, or put another way, if I can build a good enough model, right, if I have enough knowledge and, right, so it's not necessary that I, learn, for example, certain operating points from the data, then I'd rather use this model. And then exactly, I also understand how to transfer this rule to a new environment. For example, if I transfer some rule which I've based on operational experience from a network deployment in India to a deployment in Germany, right? I need to look at, different usage patterns. I need to look at, different bank holidays, or I don't know, right? So, so typically when you can create a rule, I think it's also much easier to transfer them. And then exactly if you have an ML, if you identify features, let's say with ML based, then this is of course, it's actually now a research area, which, how you actually then do this transfer, yeah? So that is of course, by nature, simply a harder problem, yeah? So, yeah.
Thank you so much. Another question is radio predictions and avoidance of failures. What could you explain the predictions and avoidance of failures? I guess this is related to your Hamburg port example.
Yeah. Yeah, like I said, I mean, the key thing to understand is here that those the measurements depicted are really, let's say, shifted by 40 seconds. Yeah, so that means when you actually, I mean, when you imagine now this barge travels and this algorithm kicks in, identifying, okay, that there is or there will be this drop in RSRP, then of course you can actually trigger at that point in time. So it means at that point in time, which is identified here by this vertical line here, at that point you do actually the change in the network configuration, yeah? And that allows you to overcome this future anticipated radio link failure, right? So this is really important to understand, yeah. And like I mentioned, of course, we don't claim now that this, you can always do this, right? Simply because of the specifics of the user population, of the specifics of the deployment scenario. But of course, it has the promise that certain things we can avoid. The other action, by the way, you always have to think about this two domains, right? So the network domain and then the surrounding environment. You could also avoid this, for example, by triggering in this vertical line, to trigger the barge to take another route, right? So that would be a reaction in the physical domain, right, and not a reaction in the network domain, yeah? Which is, by the way, something you can imagine also for AGVs, right? So if you either anyway by some detection that there's a shadowing in a certain area, or you predict it because you have actually the necessary data to do so, then of course you can change your AGV path. Yeah, why not? Yeah? In principle, right? Of course, you need to have the interface and all the technology to do so. Yeah?
I think that's a very good answer, Henning. I think this goes back to what Stefan was asking earlier as well about the actions that you take. I had this question, but I thought it was a stupid question to ask.
No, it's actually a very good question, because, I mean, if you say you have two domains, let's say the network domain is, let's say, on par with this, say, application domain, then you could choose either way, right? But of course, for example, we as a network vendor, if we tell an enterprise who, okay, now please take a different route because here the network coverage is so bad, then maybe it's not a good impression, right? So therefore, of course, we think more about action in our domain. But I think for me also the beauty of this this kind of, say, cyber physical systems, or say applying network technology in the domain of, or let's say, for particular campus networks, is that of course you have certain more control about what your application, your system is doing, rather than in the public network scenario, right? So in the public network scenario, you cannot just tell people, please go somewhere else because I don't want to change my radio configuration, right? So, but here you have more degrees of freedom in that sense, yeah.
Thank you so much. Maybe one last question. We are not going to cover everything, but there is a really nice question from Ajay, if I am pronouncing the name correctly. The question is about the role of AI ML in general. I mean, I had this question as well after looking at your slides, Henning. So in terms of modeling, in terms of prediction, yeah, it is right, you are using AI ML, but in terms of autonomy as such, what are your comments on the role played by AI ML in both in terms of digital twin or the modeling aspect, or in general about predictions for taking actions, or predictions for in general increasing autonomy?
Yeah, maybe if you want me to answer very bluntly, you could say, even I or my team doing research there, I mean, when you have a model, and you should avoid AI, of course, right? When you can describe a good enough model, don't do AI, right? But for problems where this model creation is too complex, or encoding this model and maintaining the model over time is too complex, or too let's say work intensive, or sometimes, like I mentioned, there are also like new use cases is not even possible, then I think there's no way around, right? But like I said, one key message from my talk is that actually when we talk about AI, I mean, AI essentially is an enabler for this axis, right? For that axis that in a way only tells, I mean, what is the separation between the machine and the human in the system? Because we never can simply say AI does all the job, right? There's always some, in a real system, some framework. Like I said, in the most advanced case, we need to at least tell the user, what is happening, provide us explanations. So it means it's always a combination of this in AI enabling plus this instrumentation towards the human, towards other systems, right? Toward let's say the outside, yeah. So that hopefully answers the question.
Thank you, Henning. I know you have meetings, and I know you're a busy person. So thank you so much for taking the time. There are several questions in the chat window. It just shows that this topic is really interesting. We hope to engage the participants in the Slack channel. So we request everybody to come back to us in the Slack channel, and I will note these questions and put it to you as well, Henning. So thank you so much for patiently answering these questions and staying with us. And once again, it's a really excellent talk. Over to you, Thomas.
Thank you so much, Vishnu, for the Q&A, and thanks a lot to Henning for taking care of the webinar, for presenting, for all the time, for this interesting talk. We really are grateful for your time to give us this webinar. At this point, I would like to thank all colleagues, everyone who participated in today's episode in the webinar series brought to you by the ITU AI and Machine Learning 5G Challenge.